Hello AP Physics students, this is Dr. Brenzi, and this is an example of a problem you might encounter in lesson 9.5, which talks about damped oscillators. So in this example we have a mass of 1/2 kilogram that's attached to a spring whose spring constant is 200 newtons per meter. And we're being asked what is the angular frequency of this damped system if the damping coefficient B is added to the system, so a damping force with B equals 10 kilograms per second. And if you might remember from our lecture, that damping force F is equal to negative B times V. So they're really talking about that coefficient B. And then part B tells us for what value of B is this system critically damped. Okay, so let's talk about each of those things here. Okay, I'm just going to go ahead and write down some givens here. One of the things that was given to me in the problem is that the mass is 0.5 kilograms. Wow, I just wrote all of them down here. And then that the spring constant is 200 newtons per meter. And finally, that force constant, that damping force constant, is 10, and its units are kilograms per second. You're actually going to have to do a problem where you actually prove that those units are kilograms per second for that coefficient, but I'll leave that for the homework. The other thing I need to know is, first of all, asking me for the angular frequency of a damped oscillator, and we learned in class that angular frequency of a damped oscillator is given by this omega, and it's equal to omega naught squared. And omega naught squared, if you remember, is the undamped frequency of the oscillator, that mass on a spring. And then we have to subtract from that this term B over 2m squared, which causes the angular frequency to actually get smaller. Okay, so let's remind ourselves omega naught. So that's what the angular frequency would be for an undamped oscillator, a mass on a spring. So that's the square root of k over m. But I know in my equation I want omega naught squared, so why not just go ahead and calculate omega naught squared anyway, especially since in order to get omega naught I have to take a square root. So it makes sense to actually just figure out what omega naught squared is directly without taking the square root. So omega naught squared happens to be k divided by m. So if I take 200 divided by 0.5, I get a value of 400 for omega naught squared. And then I can ask myself, okay, what is B divided by 2m squared, which is the other term under the radical here. And so I plug in those values. 10 divided by the quantity 2 plus 0.5. Well, the denominator happens to be 1, so I know that this value is 100. Okay, and then I actually have to go to the next slide in order to figure the rest of this out. You don't necessarily need to do that, so let me advance my slide here and rewrite that equation. We just figured out that omega naught squared is 400, and B divided by 2m is squared is 100. So that means that the angular frequency of this damped oscillator has to be the square root of 400 minus 100, or it ends up being approximately 17 radians per second. Alright, so that's an example of how you might use damped oscillations or a damped oscillating system to figure out certain properties of that system. I hope this video was helpful and look forward to talking to you soon. Bye.